let us continue our quest on understanding randomized algorithms. Remember, we have started discussing algorithms, specifically quantum algorithms. We saw Deutsch algorithm, we saw Deutsch-Jozsa algorithm, but in both these cases, they were very good for a separation between deterministic and quantum computation, correct? For example, for Deutsch-Jozsa, you needed only one quantum query. But classically, you would need n by 2 plus 1, right? Lot of classical deterministic queries. Though we also saw that if we want a randomized algorithm for this Deutsch-Jozsa problem, that's very, very simple. We just toss some coins, and if the function is balanced, we will see 0 and 1 with high probability. Given the quantum model is probabilistic in the sense that measurements are probabilistic, we would want to compare quantum with what kind of computation? Randomized computation, right? So we want to compare quantum versus, so this what about randomized versus quantum? But then we would first like to understand what are randomized algorithms, right? And this is what we started in the last class. We saw that randomized algorithms are basically you have your original algorithm and a random string as another input, correct? We remember that. A randomized algorithm takes two inputs, the original input and a random string. And what do we want? We want that the behavior of this algorithm is nice with respect to almost all R's, correct? This we can quantify in two ways. We can say that for every R, my answer should be correct, but then the cost will only be the, what kind of cost will we take the worst case? No, we will take the expected cost, right? So generally when we talk about algorithms, right? This is my cost, worst case cost. That's how we consider in our algorithms. So in this case, it would become max x comma r. Okay, but we say we will relax this. Instead of this, again, performance will always be worst case with respect to x, with respect to the input. What we are saying is that on some R's, my performance is pretty fast. The expected amount of time I will take on most of the R's is actually small, correct? This is what's called the Las Vegas model. But the main model, the main relaxation is when we still consider this cost, but then we say that algorithm only need to be correct on large fraction of R's, right? Again, for all X, my algorithm should be correct for large fractions of R. And this was the main model. And obviously, I had not defined what large fraction of R meant, correct? Then we saw that if we talk about functions with two outputs, we had two ways in which we can quantify error. We can say what large fraction means. If we are talking about one-sided error, that means on one side we are always correct, then we say that the error should be less than 1. Any constant less than 1 error. So even if my error is 0.9999, it's still okay if the algorithm is one-sided. And obviously you had a question in the midsem about it, and I hope that is clear now. So this is important. On one-sided, the error could be as big as possible. It should be a constant less than 1. If we talk about two-sided, then for two-sided or bounded error model, the epsilon should be less than half, because if you are erring on both the sides, creating an algorithm which succeeds with probability half is trivial. You just toss a coin, say 1 or 0. You don't have to know about anything about the problem, anything about the input, you just toss a coin. Correct? So then, now these are our definitions, and this will stay true even for quantum algorithms. And generally, we will talk about again bounded error, and we will say that our success probability should be greater than 2/3. We will keep this as the standard, but 2/3 is really not important. We remember that, right? Even if it is 0.55, I am happy. With some repetitions, I can make the success probability to be 2/3. So I will keep switching between success probability and error probability. Correct? So this is, in some sense, 1 minus epsilon, where epsilon is the error probability. Right? So this should be greater than half. Right? And in terms of places where randomized is advantageous, we already saw an example. We saw calculating pi. But today, I'm going to give you another example, which is computing a function like this, and this is going to be our model of study for a lot of time. So how do we show that if you want to compute a function like this, randomized can do better than deterministic? Okay, that's the example we are going to start with, and then we will move on to quantum versus randomized. But first, if randomized is same as classical, then we are not worried, right? So let's first see why randomized is an interesting model of computation. Okay, so the problem is clear. We will find a function. I will give you a function such that it's going to be difficult to calculate its value if you have to do it deterministically, but classically you will only look at very much lesser bits as compared to the deterministic ones. Okay, clear? So let us start. The function is going to be what we call recursive majority, but it is instructive. Let's do some exercise with the smallest function. Let's say this I will call majority on 3 bits. And what is this? What do you think majority on x1, x2, x3 should be? So n equal to 3, x1 is 0, 1, x2 is 0, 1, x3 is 0, 1. At least 2 of them will be either 0 or 1. Correct? So majority is clear. Correct? Function is fine. This is the function we want to compute. Okay. Now, if I want a deterministic algorithm where I want to succeed with probability 1, there is no randomization, how many bits will I have to see in worst case? Do you have to, in worst case, deterministically? All. Correct? So, because any deterministic algorithm, if you look at bit xi and xj, I can make sure that first bit is 0, second bit is 1. And if I don't give you third bit, you have no idea what the majority is. So no algorithm which only looks at 2 bits can answer correctly on every input. This is quite clear, right? So whatever be your algorithm, you pick 2 bits of your choice. I can keep them, one of them 0, another bit 1. Then you can't tell me what the function value is. Right? So whatever be your algorithm, it has to look at all 3 bits. Correct? This is quite clear. Right? Now, so we want to reduce this number. Any idea how can we create a Las Vegas style algorithm? And then
both of them are the same probability, and if not, then we have to.
very good, right? So this is very simple idea, right? But this is not very difficult. It is saying there are 3 bits. If all 3 of them are the same, let's say 1 1 1 or 0 0 0, I query only 2 bits, I will know my answer. Correct? In the other case, when there are, let's say, 2 bits are 1 and 1 bit is 0, what happens? If I select 2 random bits with for how many pairs will we see 1 0?
For 2 pairs.
For 2 pairs, right? So with 2 by 3 probability, I will have to look at how many bits?
The 3rd bit.
All the 3 bits. But as Suyash very nicely said, there is one case where we actually save. Correct? If this is the case, if I see both ones, then I know my answer is 1. And notice this is going to happen in every case. This is the bad case in some sense, right? So then, what is this? All of you have cleared some kind of exam, right, to be here. So I'm sure you can do this. Sorry? Oh yeah, perfect. Good. 3, right? So, okay. What I wanted to write was 3. My 9 is equal to 3. Correct? So then we have a saving. Okay. Now this might feel like, oh my God, that's okay. We were allowed to err. But now if I had asked you to create a Monte Carlo algorithm directly, what would it be? No. If you never look at it, then yeah. So what would you do?
We will never be sure if by looking at 2 and they are different that we have got them.
But the error probability one can't get better than half, right?
So in Monte Carlo, we'll be only looking at, let's say, 2 bits, but then we will have a certain uncertainty, the probability that we are not sure that the answer is correct or not. Sometimes we know that the answer is correct for sure. Sometimes we'll assume, let's say we see only 2 bits, 1 and 0, and then we say, okay, I'll just assume that the answer is 1, but then that is with half certainty. So then there is that. So in Las Vegas, like I just wanted to confirm this, in Las Vegas, we have 100% certainty that this is the answer, but we are just reducing the cost, which is better than the properly deterministic algorithm. In Monte Carlo, we are reducing the correctness, but we are also
relaxing the correctness.
Relaxing the correctness, but we are also reducing the cost at the same time.
Reducing the cost is the ultimate option. Yes. So finally, but then this doesn't seem obvious, at least at this point. That how will you create a Monte Carlo algorithm here? Huh? Huh? Again, we talked about it last time also, this reversing doesn't work. You keep doing that. Again, your algorithm should work for all inputs. We have to consider all x's. Whatever be your algorithm, it should work for all inputs. So the error would be half. Because with half probability, So the error would be 2 by 3, right? Because let's say, okay, what is your input? You look at 2 bits. If both of them are equal, what do you answer?
If both of them are equal, we say 1.
You say 1. Okay. If okay, so remember, fix your algorithm first. Okay, you query randomly 2 bits. If both of them are different, then you say.
If both of them are 0, then only we say no. Except that we say yes.
Except say you 1. You say 1.
Yeah.
Now let's say this is the input. With 2 by 3 probability, you will see 0, 1. In both the cases, you will answer incorrectly. So for this input, your error is 2 by 3. Correct? Sounds good? Good. So yes, it is one-sided, but then why did we say that error less than 1 is fine? Because we did not care about constants there. This one, what was the whole argument? Why did we say that 2 by 3 and 3 by 4 are similar? Because we could repeat it sometimes, constant number of times, and still things remain the same. And this idea we will use. But here we can't use this idea. Because as soon as you repeated this algorithm, even twice, your number of queries has become 4. So, your error probability is 2 by 3. Correct? Ideally, your probability should be this success probability. So you want to reduce this to this. But as soon as you repeat it, your number of queries has become bigger, more than 3. Sorry? You can be incorrect with 0, like you can be incorrect with all the probability, right? Or something. Again, the point is this repetition will kill you. So
if it is like 110, then if we look at 1 bit, then the probability is that with 2 by 3 we would choose 7. And if it is 0,
okay.
probability that it means 1 by 3.
Sure. So I change my standard here, make it 3 by 4. The point is, you won't see, I can just change this probability here and make you get stuck. But now I will do something and suddenly this advantage will be very clear to you. Okay? So let's do this thing. But no. See, okay, you always have to remember the reason why we say something. You can't have this blanket statement that constants do not matter. Like these do not matter. These do not matter in the asymptotic setting. Why did we say that 2 by 3 and 3 by 4 errors are similar? Because you can repeat it and there is a constant multiplied by n. But there is no n here. We are talking about a function just on exactly 3 bits. You repeat it here, your complexity will become 4 or 5. You are comparing between constants now. So obviously constants matter. Right? So then clearly the idea is I should make this problem where my n is growing. Okay, so this is the point I'm trying to emphasize, that anytime you try this repetition trick with querying 1 bit, querying 2 bit, if you want to amplify the error, you will get into a problem. So you have to construct first a problem where instead of 3 bits, you want n bit function. Okay, and that n bit function is going to be a simple recursive function. So
in this particular case, we cannot in this particular question, we cannot reduce the error down from 2 by 3, right?
We can, but then we can't say that error 2 by 3 is same as error 3 by 4. Or error 3 by 4 is same as error 4 by 5.
No, but in this particular question,
yes,
without repetition, because repetition would make it redundant, we cannot reduce the error less than 2 by 3.
So yes, you can reduce the error
with 3 bits.
No, with many more queries.
Yeah, so with many more bits in the question.
Yes.
But in this particular question where you said majority of 3, it's not going to be less than 2 by 3.
Yes, yes. So in this kind of question, if you want to reduce, let's say, array to the 3 by 4, then I will get into trouble. Then I would want to query more than probably 3 bits or something. So that's not what I want, right? So then I should create a function which has n bits, and the simple idea is I just repeat this function multiple times. What it means is so if it is d levels, then I have 3 to the power d inputs. Okay, so what do? I will apply so I have 3 to the power d bits. I divided them into bunch of 3s. I apply majority. How many outputs will I get? I have 3 to the power d inputs, 3 to the power d minus 1, right? So there are 3 to the power d minus 1 majorities here. 3 to the power, so all of these will give 1, 1, 1. Now these 3 to the power d minus 1, I will again divide them into 3, 3, 3, 3. 3 to the power d minus 2 outputs. Keep going on, the final output is my answer. So this is a function of this kind, and clearly I am getting it from here, and here I will have significant savings. So I will keep this because we would want to compare with these. Okay, sounds good. And if you want to understand it in a different way, let me call it FD. What is FD? I can define it inductively or recursively, whatever you want to call it. So this function definition should be clear before we go ahead. What are we doing? We are saying, so how many inputs are there for F2? How many inputs are there for F2? 9, right? What will happen for F2? I will divide them into 3, 3, 3 punch, apply F1, 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 which is majority, right? For F3, I will have 27 inputs, correct? Take the first 9, apply F2 on that. Take the next 9, apply F2 on that. Take the next 9, apply F2 on that. I get 3 bits, apply majority on that. So first question is this function definition clear? Because otherwise, how can we prove the difference between randomized and classic deterministic? Questions about this function definition?
F of 1 is majority.
Yes.
Sorry, F of d minus 1 is exactly.
So I will define. I'm defining this recursively, right? So f of d minus 1 will be same structure. You will have a majority here, then f of d minus 2.
Okay.
F of d minus 2 will be majority 3, f of d minus 3. You keep going on.
That's the same tree, but just defined in a different nomenclature.
Because I want to make sure, so this defined inductively, this is fine now, right? I have defined the base case, I have defined how the D level is, right? So by induction or by recursion, this is a complete definition, right? Other way to understand the same function is, you take the entire input, divide them into groups of 3, apply the function, you get 3 to the power d minus 1 inputs. Again divide into 3, apply majority, you get 3 to the power d minus 2 inputs. Keep doing it, finally you have 3 inputs, take their majority, that's the answer. whatever way they are the same. Okay, this is called the recursive majority tree of D level. If you expand this out, fd minus 1, apply, then it will look like this tree. It will have majority 3, 3 majority 3 gates here, 9 majority 3 gates, 3 to the power d minus 1 majority gates at the bottom.
So majority of D what?
Of height d. Height d. Fine. If this is the case, if you understand it, then first exercise is prove deterministically that we need to look at all inputs. So the number of inputs I have to see deterministically is actually 3 to the power d. Prove it. How will you prove it? It's the same point. Suppose you have not queried just one bit. Can you say that the function value is undefined? How? Again, you're applying randomization here. Yes.
So we can have that at the top we have 0, 1, 0, and the 0 goes into a 0, 1, 0, 1 goes into 1, 0, 1. So like
No. First, you have to argue in the adversarial way. I give you an algorithm. You ask me there is one bit which you have not queried. Where is that bit? It has to be in. Why does it have to be in AND? I might ask x 3 to the power d in the beginning, no? I have all these inputs, right? Nobody is stopping me to say, oh, give me this bit first. Then this bit, then this bit. That I am allowed to do. Or probably I check x1 next to and I decide, oh, I'm not going to query anything here, I will query here. But whatever you do, there is one bit which you have not queried. Correct? That bit will fall somewhere here. Correct? Now, by induction again, I will assume that if this bit has not been queried, then I can't answer this on some input. So then, set its input as you were doing, 0 and 1. Now, since one bit is unqueried here, by induction, I can't answer. There is one input where I can't answer here. I have fixed that input here, so I don't know the answer here. So I don't know the answer in the overall thing. Okay, this is just, I think, just going through the definitions, but the idea is clear, right? That intuitively it should be clear to you that even if there is one bit which you are missing, I can set rest of them so that your answer is not determined. Correct? Sounds good? So, or other way to, or if you want again in a very, very direct way, let's say if there is one input where even if you take the last input bit, you don't know what the answer is. Okay, so I will keep answering according to this in all three. Okay, so till 3 bits are left here, till at least 1 bits are left here, you don't know the answer there. If you ask the last bit here, I will first set 1 to 0, second to 1. Still you will have 1 bit. If you don't know that bit, you cannot answer what is the overall thing. That's a hint, but that's not proof, right? Do you want an example to understand this?
so if we have a string like 0, 1, 0, 1, 0, 1, 0, 1, 0, that we have to check the last bit to find out where it ends.
See, this is what I'm trying to tell you, Suresh. You don't understand it in an algorithm. You don't have to access in sequence.
So, but
You have
deterministic was that thing, right? That we have.
no, in deterministic, you are not using randomness to decide which one you are doing. But I can say my deterministic algorithm is query the first bit, query the third bit, query the fifth bit. That is still deterministic. I haven't decided randomly which bit I am querying second time. Right? So if you say that your fixed input is 0, 1, 0, 1, 0, 1, 0, 1, 1, 2, 3, 4, 5. This, I can say that my algorithm queries first bit, third bit, fifth bit, 7 bit, 9 bit. And now this deterministic algorithm works very fast for this input. So you cannot give me an input irrespective of the algorithm. You give me an algorithm, I will construct an input on which your algorithm will fail. It has to be this way. That's what I'm trying to emphasize.
For deterministic, we know that it will always query the first, third, and fifth, like that. Right?
No. There are 1 million deterministic algorithms. One of them could query first bit, second bit, third bit, fourth bit, fifth bit. One of them could query first bit, third bit, fifth bit, seventh bit, ninth bit. There is not just one deterministic algorithm, right? And what you want to say is that you pick any of the deterministic algorithm, there is some input where you will fail. If you have queried only 8 bits. And this is not a difficult thing to convince yourself. It is clear, right? If you look at, if you are choosing this, what I will do is, I will take now input 0, sorry. If you take this, I will take the input as 0, 1, 0, 1, 0, 1, 0. Correct? And now I am failing or something.
Just wanted to ask, so I just was trying to visualize something. If there is one more layer beneath this, like f of d minus 2, and let's say that layer has all the numbers in it, below f of d minus 1. If we first compute f of d minus 1 and we find out that it is 1,
yes.
then we compute the second f of d minus 1 and then we compute that this is also 1. So we don't really need to compute the third f of d minus 1, right?
That is true. So you have a deterministic algorithm or a randomized algorithm.
So so this is deterministic though, right?
This is deterministic, but the point is your deterministic algorithm has to work for every input.
Yes, so what I am thinking right now is, even though there are, let's say, 2, 3 more layers down the line,
Yes.
we will go, what I am thinking is, we will go from left, like it's depth
So you-
search kind of, but from the bottom.
So you first calculated this.
And first, let's say there is even one more layer beneath that, and then there is some numbers.
Okay.
F of d minus 2, and then there are some numbers.
So one more layer.
One more layer, and then there are some numbers. Yes. So in the bottom left one.
You are doing a deterministic algorithm now, right?
Deterministic algorithm. Bottom left one, we calculated that because we have to calculate that. Then I also calculated the next one.
Bottom means you calculated
That one.
this one.
Yeah, the exact bottom left one. Not the first half of that. The first half of the circle sum.
Okay.
Yeah, I calculated that first. I calculated the next one first. If both of them are matching, I just send the answer to the above one as that same answer. If it is not matching, then I see the third one, and then I send the majority, that one. Then I do the same. I have the answer for the first majority. I have one of the inputs.
See, so this is your algorithm, right?
Yes.
Now I will tell you an input where you always have to query all the bits. I will set the bits so that this is 0, this is 1.
Right.
Then you will have to query the third bit.
Got it.
If your algorithm was query this, there is an input where this is 0 and this is 1. Then you have to query this.
So there will always be a worst case scenario.
There will always be an input where you will be forced to look at all the 3 to the power d inputs.
Right.
And so this is not hard to convince, but then you can formally give its proof using induction. That's what I'm saying. So I'm not saying that your deterministic algorithm will always take 3 to the power d queries, but for some input, it will have to look at all 3 to the power d.
Got it.
Whatever algorithm you create, I can set my input in such a way that you will have to look at all 3. All 3 to the power d. Yes.
Proof for induction, we also have to say that, like, for the left bit to be 0, we also have the 3 branches where 0 and 1 are met, but the third bit has to be middle one has to be read as 0 for this to become 0. Right? Like we can, like for the central one, you said that we split it into 3 again.
See,
but even the left and right ones, we have to do.
We don't have to do that. That's the power of mathematical induction. I don't have to go into that argument. What I can say is now, clearly for majority 3, I need to take 3 bits. Now, what I will assume now is that fd minus 1, if I want to compute fd minus 1, there is whatever be your algorithm here. See, the algorithm here, algorithm here, algorithm here are independent. There is no mixing here. It's not like a bit here can affect this, a bit here can affect this. So what I'm going to say now is, look at your algorithm, how it is working in this left part. I'm going to, for that algorithm, there is one input which will take all 3 to the power d minus 1 in queries. I'm going to answer according to that. I know finally what it will do is it will unravel it in fd minus 2, fd minus 2.
Like, because we can show for the central case, we know that for the left and right case also it will take at least, like all of them will take 3 queries for some inputs.
All of them will take 3 to the power d minus 1 queries.
Okay, yeah, like, okay, as an individual, take 3 and then those
3. Right. And I have just said that, oh, the last bit you queried was coming from here, but wherever it is coming from, the others I can set like this, right? So induction just makes it easier to write it down on the paper. Okay, but the intuition is, whatever be your algorithm, I will keep setting my bits so that it always was the idea of Swayash, it always has this 0, 1, 0 structure. Whatever you have not queried will be the answering bit. Okay, so that you can always do. Clear? Okay, we can write this argument down formally also if you want once the class ends. I think you should try to write it down. If not, I can write it down for you. But you will require, but it's intuitively it is clear that we will require 3 to the power d, right? Whatever be your deterministic algorithm, there is some input on which it will fail if you look at only one less query than 3 to the power d, right? So now we ask, what happens in the randomized case? What should be the randomized algorithm? Now you know, you have seen F1. What should be your randomized algorithm? What was the randomized algorithm for majority 3? You chose some 2 and figure out their answer, right? So what should be the randomized algorithm for such a structure?
For each of them we apply the randomized algorithm.
Pick 2 trees at second level, compute their value using the randomized of d minus 1 depth. Correct? Finally, I will compute their value. If both of them are same, I am done. Otherwise, I calculate the third one. Isn't that the natural extension of what you did for majority 3? For majority 3, you said, look at the 3 children, pick 2 randomly, see if they are equal. Now, what are the children here? Fd minus 1. So, you pick 2 randomly. Let's say you picked this and this. Then you've picked first and third. You say, apply my randomized algorithm here, apply my randomized algorithm here. Correct? Finally, I will either get 0 or 1. If both of these are same, then I am done. If they are not same, then I look at this. Right? So let's say the worst case cost for a d minus 1 tree, d minus 1 level tree is cd minus 1. Correct? Now, if the input x was such that fd minus 1 was like this would be the favorable case. What will happen? I will pick 2 of the fds here. What will be the cost for that? 2 times CD minus 1. So CD of x will be less than 2 times CD minus 1. So CD minus 1 is the worst case cost, right? Right? So now what happens? Why am I saying worst case? The cost, sorry. Worst case for, okay, so I should say worst case over x, right? This is the cost. Now suppose your entire 3 to the power d input is such that fd minus 1 is 1, fd minus 1 is 1. So in this level, I am getting 1, 1, 1. Right? Now what will my algorithm do? It will query some 2. But after the 2, it knows what the answer is. It doesn't have to query the 3. So it will solve 2 fd minus 1s completely. That's 2 times cd minus 1. Because cd minus 1 is the max over all x's at this level, fd minus 1, right? Sorry. Sure. Yes. Less than equal to. Yes. Correct. If this was the bad case, what will happen? We have done this analysis. Now what will happen? With 2 by 3 probability, I will have to look at 3 times CD minus 1. All 3 children. But the saving would be 1 by 3 times. I will only look at 2 times CD minus 1. This is clear? So this is the same analysis which you did for F1, but now there are trees attached. So previously the cost was 1, I am replacing this by CD minus 1. Okay, so then what you know is that whatever be your x, sorry, I don't even have to put x, 8 by 3 CD minus 1. So that means right, because CD was CDX for the worst case x, right? If all of the CDX are less than this, then the maximum is also less than this quantity. Correct? So then and now you see deterministically correct? And if you have gone through your computer science courses nicely, you know that 3 to the power d is always bigger than any constant times 8 to the power 3 for this is our 3 to the power d goes much faster asymptotically faster than 2 to the power d. 3 to the power d grows much faster than 8 by 3 to the power d. So this is fine, right? These are different asymptotically. So now whatever constant you want to do for array amplification, still deterministic cost will be higher than the randomized cost. Okay, and
this analysis we did here like 2 by 3, like 8 by 3 power d. This is for the unlucky case like 0, 1, 0.
yes, yes. But then we want worst case for all x, right? So we have to bound on worst case. Yes.
And if we are lucky and get 0.0001, then these analysis.
But that's immaterial to us because our cost has to be worst case over inputs. Because otherwise, if you're saying, oh, in lucky case, then there are deterministic algorithms which also take only to the power d or queries, right? So that is, we are comparing worst case cost for all x. Right? So you are right that for some x's, the cost might be smaller. For some x's, it might be high. But even the worst case cost is bounded by 8 by 3 to the power d. That's the statement we need to make and we have made. Right? So the cost deterministically, if you want to be correct on all the inputs, was 3 to the power d. Randomly, it is 8 by 3 to the power d. Correct? But this is the expected cost. Okay?